Hello and welcome to this lecture on fracture mechanics applied to design. This will be the last lecture in this particular chapter where we dealt with the failure, at least static failure of materials and structures. So what I would like to do is give you an introduction to fracture mechanics in the simplest possible form, and then we would use this in two examples to illustrate how it is used at a preliminary level of design. So fracture mechanics is a very big field, and it started in the 60s where it was found that around cracks the stress becomes very, very large, and the material obviously gives in, and then cracks start to propagate. So the field of fracture mechanics is known to start at the elastic level if we want to do analysis with elasticity, and we will be able to derive conditions based on what is known as linear elastic fracture mechanics. And that level of analysis has been successful in predicting crack growth, especially in the case of brittle materials where there's no sufficient plasticity to blunt crack growth. However, when we deal with ductile materials and we design it conservatively, and we also pay special attention to areas of stress concentration, then plasticity can set in and redistribute the high stress in the vicinity of stress concentrators. And we are reasonably comfortable with proceeding without very detailed fracture analysis. For components that are very expensive or where safety is very important, we must go to a higher level of analysis using elastoplasticity, where plasticity comes into play, and we do more accurate analysis with finite elements. So at the level of this design course, we will just focus on linear elastic fracture mechanics and introduce a few concepts that can be used to allow us to determine whether a structure with a flaw will fail or not. So it is applicable to brittle materials, as I mentioned here, where we have the concept of LEFM to follow. So if we go back and look at the stress in the y direction in the vicinity of a hole, an elliptic hole, like the hole that you see here, then the stress distribution increases as we come closer to the two tips that you see here. And the increase is a result of the loss of the material in between. So the rest of the fibers will have to take up the force. And at the end, we obtain an expression for sigma max in the y direction, sigma y max, close to the tip. And this expression is shown here, that the maximum stress is equal to 1 plus 2 times A over B. All of this is multiplied by the nominal stress sigma. So this is nominal stress. And nominal, it means that it is applied far from the disturbance or the hold. As a special case, we probably know from strength of materials course that if we have A is equal to B, we have a circle, and in the case of a circle, sigma y max is 3 times the applied stress. So that's kind of a very simple and a special case, and it's used, we can derive it as we did in a strength of materials course before you get into our design course. Then we set up the equations for elasticity and use area stress function, and then we find the stress concentration factor, which in this case is equal to 3 when it's exactly equal to a hole. If now becomes an ellipse, then the situation is worse, because depending on the ratio of A over B, then the stress can be very large. For example, if A is much larger than B, like we have a very sharp ellipse like that, then the sigma y becomes very, very large. And in fact, when we do analysis for cracks, the cracks would be a limiting case of this idea of an elliptic hole, where we consider the crack to be a slit, but then the radius of curvature of the slit at the ends is not finite, but is zero, essentially zero. So when you have a zero radius of curvature, that's a very, very sharp crack. And when you have a sharp crack, that's a discontinuity of the material. When you apply the previous formula, you have the amplification factor is 1 plus 2 times A over B. This factor becomes infinite. Therefore, we need to kind of understand a different method of analysis for the stress intensity close to the crack tip. So before we get there, let's see that we consider the different modes of fracture, and the modes of fracture is mode means method of fracture or crack propagation. We have 3 modes. As you can see here, mode 1 is called the opening crack mode, and the opening crack mode is due to a tensile loading. So this is mode 1 is right here, where the crack is perpendicular to the loading direction. And then we have mode 2, which is called the sliding mode, and the sliding mode is due to in-plane shear. So if you have a shear stress applied in this direction here, then the direction of slide for the crack is going to be along this direction here. And this we would call mode 2 crack. And then finally, there is mode 3. It's called the twisting or the tearing mode. And this is due to out-of-plane shear. So we have 2 types of shears. One is in plane, and the other one is out of plane that we would consider. When the shear direction is out of plane, then the motion of the material will be along the direction of shear, and we get at the crack tip a twist that we will call mode 3. So these are essentially the 3 different modes of fracture that we would consider. Now, if we look at the stress field around the crack tip, if we consider a crack in an infinite medium, then the crack in an infinite medium, we can set a coordinate system, and the coordinate system would be at that tip. And one of the easiest coordinate systems that we can consider is a polar coordinate system, where we would have an element here, and an element is described by the angle theta and the distance r from the crack tip. So let's take the width of the crack to be equal to 2a, and then on that element, if it is oriented, let's say we're gonna orient it such that it is oriented with give us the opportunity to have an x stress sigma x and a y stress sigma y. This is a 2D plane strain case, and also we have a shear distribution along the edges here tau xy. So we have three different types of stresses on that element. Without going into the derivations, because we have to pay attention more to the application in the design course, we find that sigma x is equal to the square root of sigma times the square root of a over 2r. And then, so this is kind of the radial dependence. And then we have a cosine term, cosine theta over 2, and that is multiplied by 1 minus sine theta over 2 cosine, sine, another sine 3 theta over 2. So the stress field in the vicinity of the crack, the idea here is that it is it goes as 1 over the square root of r. So this is what we call singular. So singular means goes to infinity. And therefore, we are not able to obtain a realistic stress value close to the crack tip. So we're going to reorganize this formula to allow a better redistribution, as we'll see here. And if we take, we let the product of sigma times the square root of pi times a to be equal to a constant or a parameter. And since this is a crack in mode 1, because we have applied stress far away in mode 1 perpendicular to the crack face, then we're going to call this K sub 1. And we're going to call or define K sub 1 as the stress intensity factor. So this is the SIF, stress intensity factor. So if we agree with this, then all what we have to do is put a pi here and a pi down here. And in this case, the formula would be just here, K. We can apply the formula for the stress intensity factor with K sub 1 defined as sigma square root of pi a. And it's the same formula for sigma x, that on the top we have the stress intensity factor, and in the bottom we have the square root of 2 pi r. And again, we have cosine theta over 2, and we have 1 minus sine theta over 2 sine 3 theta over 2. Similarly, if we look at the stress in the y direction, the only difference is that we would have a plus in the arguments here inside the parentheses. And if we look at the shear flips from cosine theta over 2 to sine theta over 2, and the sine becomes cosine. So all of this comes from analysis using an Airy stress function, for example, in elasticity. Since we have a two-dimensional stress system, then we have to also specify whether we have plane stress or plane strain. In case we have plane stress, then the third stress, sigma z, should be 0. And in case we have plane strain, then epsilon z, we set it equal to 0, and this gives us the condition that sigma z is just nu times sigma x plus sigma y. Most of the design applications are based on plane strain, because a plane strain, it means that you have a structure that is reasonably thick. So this is thick here, and therefore we use plane strain. In case we have a structure that is very thin, like a sheet metal, for example, then we must use plane stress and make some modifications. So we'll leave this out for now, because we want just to focus on plane strain conditions and applied to different designs. So let's now move on to understanding the remainder of the idea of fracture mechanics. And what we have done so far is wrote the equations for the stress field for a crack in an infinite medium. So there are no boundaries for that crack. However, in reality, we have cracks in structures. It could be center cracks, it could be off-center in the structure, or the crack could be on the edge as well. So we can have edge cracks. And for these kinds of situations, many people have done analytical calculations or numerical calculations for the stress intensity factor, and they found that the stress intensity factor K sub 1 is somewhat different from the case of a crack in an infinite medium. And in order for us to get an idea about the size effect, then we're going to modify the stress intensity factor and multiply it by a modification factor, and we're going to call this the stress intensity modification factor beta. And once we have that, then the stress intensity factor is written such that I have now a situation where the K is actually equal to beta times sigma times the square root of pi a. Previously, we wrote it as K sub 1 for an infinite medium as equal to sigma square root of pi a, and the units of this is megapascal square root of meter or KSI square root of inch. So these are the two different types of units that we use for the stress intensity factor. The beta here is a shape factor. Shape factor, or they call it stress intensity modification factor. And these you'll find it in many design manuals or design books. So I'm going to show you a few examples on the beta factor, the shape factor, and we will just go a little bit slowly over these examples so that you'll be familiar with them. And then when you have a design application, you can go to the manuals where you can find the beta and apply it for the particular design. So let's review here some of the stress intensity modification factor for shape factors, beta. And what you see here is a crack that is off center, and the distance of the center of the crack from the edge is d, and the crack size is always 2a. So the size, when you say size, we know it's always 2a, and the width of the specimen is 2b. So we have three parameters, d, a, and b, and therefore we should be able to find beta as a function of three parameters, three variables. Well, it's kind of not really useful to have a three-dimensional surface, so what we do is we just plot beta as a function of one of them, which is usually we take one of them, like d for example, and use this as a normalizing ratio. So if we just plot beta as a function of a over d, and then we take different values for d over b, then we have covered the dependence of beta on these three parameters, d and a and b. So let me just follow an example. You find the three solid curves here and three dotted curves. The solids are for one tip of the crack, which is tip A. So this is, we have a stress intensity factor for tip A, and the dash is for tip B, because the stress, if you have the tip of the crack close to the edge, it's more dangerous, so you have higher stress intensity factor. So that's one of the design curves that you will see there in the book, Shigley's book. There are figures 5 to 25, many figures, and 5 to 30, 525 to 530. So we have 5 figures that cover the stress intensity factors. This is one of them, and this is 26. With 26, we have an edge crack, and the edge crack is now described by the crack length is A, is not 2A, because it's an edge crack, like a half a crack, and then the width is B, so we have a ratio of A over B, and then for different values of H over B, H is the height of the specimen, and then the specimen is under tension, and the remote stress here is sigma, while now we have a crack on the edge. The next one shows you the stress intensity factor for an edge crack, and this edge crack is can be subjected to either pure bending or bending due to forces. So when you have this is like a test, fracture mechanics test, and the fracture mechanics test is called the 3-point bend test. And in this case, the 3-point bend test, we apply a force in the center and then react it on both ends and cause a moment to fracture the material. So under these conditions, the stress intensity factor depends on whether you have a pure moment or a moment with transverse shear forces, as in the test itself. So in this case, we have the graphs illustrate beta as a function of A over H. For a pure bending, we don't have any additional parameter. For a bending associated with the shear, you have another parameter, which is the length of the supports, where the supports are, divided by the thickness of the specimen. Next example shows us the stress intensity modification factor, beta again, for a crack emanating from a central hole. The central hole has a radius r, and the width of the size of the crack is 2a as usual, but it's just kind of punctured with a hole in the middle. So it's similar to what we had before, but now we have a hole in the middle. So beta makes sense only when the crack width is greater than the hole width, and that's basically have the thresholds here. For the case of the radius of the hole is 0, this is the old case that we studied before. That would be a crack in a finite medium. But when you have holes, then you get different magnitudes of the stress intensity modification factor, or the shape factor. Two other cases pertaining to cylinders. One is a case where you have a cylinder, and the cylinder has a crack, and the crack is all the way around. So the crack is all the way around and penetrating up to a certain distance. So this is the interface of the crack. And then the cylinder is under an axial load. So we have the beta as a function of the crack size divided by the thickness of the cylinder, and for different value ratios of the inner to the outer radius of the cylinder. So this example and the next example are used in a pressure vessel design. So when we have a pressure vessel, for example, we have an axial crack, and the axial crack goes all the way along the cylinder. So the crack is actually going from the surface of the cylinder, going in a little bit, and then it's a little bit hypothetical case, but it's just available numerically. Then in this case, then we have the beta as a function of the relative size of the crack relative to the thickness of the pressure vessel. So these are all examples that shows us what to compute in terms of characterizing the stress field. So we can characterize the stress field around the tip and then ask ourselves, now, is there a way to tell whether the stress applied, the remotely applied stress has exceeded a critical value? The way that is done in fracture mechanics is that we measure a material parameter or material property that is similar to some extent to measuring, say, the fracture strength of the material. But it's not a fracture strength, it's called the fracture toughness. So the fracture toughness is a material property that when the stress intensity factor it has the same units as stress intensity factor, that is megapascal square root of meter. So each material has a fracture toughness, just like it has a yield strength or an ultimate strength. And then when the stress intensity factor exceeds the fracture toughness of the material, then the material will actually fail by crack propagation. So that's kind of the idea, and let's look at the fracture toughness concept. So in the fracture toughness, we have, it's a critical value of the stress intensity factor, and it is a function of processing of the material, the temperature, the loading rate, state of stress at the crack site. So it must be understood in great detail when we do the design. So each material has a fracture toughness, and it is typically defined for mode 1, a plane strain fracture toughness. If we are considering mode 2 or mode 3, then the data become kind of more rare, and we might have to actually obtain our own data if we're working in the industry. If we're considering plane stress, then we have to do an additional kind of extrapolation of the plane strain fracture toughness to find the equivalent value under plane stress, which is usually larger. So these are all issues as you progress in your understanding of design you will meet in the future. For most materials, the fracture toughness is measured, and the measurement of the fracture toughness gives us values at room temperature. So if we go to elevated temperature, then the elevated temperature will have different values. So for room temperature, we have, for example, aluminum has 3 different alloys, and the fracture toughness is what we call on the low side, 26 to 33 MPa square root of meter. And this is the yield strength of the alloy for just kind of information. Titanium, we have 2 different alloys. One of them has a high fracture toughness and a reasonable yield strength, and the other one has a low fracture toughness but is very hard. It has higher yield strength. So later on we're going to take an example of how to select between these 2 alloys. On the one hand, one has a high fracture toughness and one has a low fracture toughness, but on the other hand, the yield strength is kind of flipped between the 2 alloys. These are fracture toughness values for steels. When you go to fracture toughness of, let's say, less than 10 MPa square root of meter, then you're dealing with essentially a brittle material. If the fracture toughness is in the hundreds, like 100, above 100, then this will behave as very ductile and great material to design with. So these are just general considerations that we have now. So for our design, all what we need to do is do 2 things. Number 1, compute this for a given load application, and then find the corresponding fracture toughness, plane strain fracture toughness from data. And then the ratio of the fracture toughness divided by the computed stress intensity factor with its own shape factor is the factor of safety for brittle fracture. Okay, so let's now proceed with this idea to apply to design. So we're going to take one example here, and this example is going to be on a steel plate, very simple example steel plate, and is going to have a crack in the center. So we're going to go ahead and find the stress intensity shape factor from the table. And then we will, if we have the stress, apply stress far away from the crack, we should be able to compute the stress intensity factor, knowing the crack size. And then we're going to compare it to the fracture toughness and see what happens. So this is kind of the simple example that we will start our discussion with. And the steel, the 30 millimeter thick, so it's quite thick, and therefore we can consider plane strain. 12 meter wide, very big, and the axial tensile stress is 50 MPa. And it's operated below the ductile to brittle transition temperature, meaning it is a brittle type behavior, and it's plane strain fracture toughness is 28.3 megapascal. So what's required from us is to estimate the tensile stress at which catastrophic failure will occur. And then we want to compare this tensile stress to the yield strength of the material. So basically, we would have to do 3 steps. Step 1 is find the safety factor for the 50 MPa. Step 2, find the stress that is larger than the 50 MPa that will cause fracture. And step 3 is then compare the stress to 240. Is it larger or smaller? So these are the steps that we're going to proceed with in the example. First step is we look up D and A, and therefore D over B is equal to 1, and A over D is equal to 0.005. And since A over D is so small, which will be right here, then we can't even read it on the plot, then we take beta equals 1. So this is easy, and therefore K is equal to beta, K1 is equal to beta sigma square root of pi A, then the beta is equal to 1, that gives us sigma square root of pi A as the K, and then when you plug in numbers, we get 16 MPa square root of meter. So now we compare that to the K1C. Obviously, K1C is larger than 16, which means it's okay. How much is okay? Then we just take the ratio, and that will give us the stress intensity factor. So it's 1.77 as a stress intensity factor. For catastrophic failure, we just set K1. So for catastrophic failure, we set K1 equals to K1C, and then recompute sigma. In other words, here K1, we just leave this as unknown. So we don't put the 50, we leave this unknown as sigma. And then recompute the sigma times something. And then equate it to K1C and solve for sigma. And when we solve for sigma, we found that the critical value of sigma is 88.4, which is less than 240. In other words, it will the alloy here that we've been designing with is really brittle because under these conditions, the alloy, the crack is going to propagate rather than the alloy yield first before the crack propagation. So now I'm going to take another example to show the yield versus cracking idea, and that's applied to the 2 alloys, the titanium alloys that we have discussed before. So we have the width of the plate, the length of the plate, and we get a force in the tensile direction of 4 meganewtons. So from all of that, we should be able to figure out the remote stress. And then the inspection showed that we have a through thickness edge crack larger than 2.7 millimeters. Usually inspection can give us much smaller value, but for this case, maybe it was visual inspection, then we find 2.7 millimeter. Then we look at the 2 titanium alloys in the table, and we know we have the K1C for each, and we have the yield strength from each one. So we have these two properties. And we want to design for a safety factor of 1.3, and the minimum weight is important. So with minimum weight is important, then we just want to determine the thickness T, because it's unknown in this problem. We have the force is known, but and the width is known, but the thickness is not known, and therefore to know the thickness we need to figure out the stress first. So we'll do that for the two different alloys sequentially. And before we move, since we have decided on a stress on a safety factor of 1.3, we have to reduce or knock down the allowable yield strength from 910 to divided by 1.3. So the allowable stress for design is only 700 MPa and not 910 for yield. So the first step is that we're going to check yielding before we get into fraction. So for yield, allowable is 700, and to find the thickness, we just know that we just equate 700 is equal to P divided by the area, and the area here is T times the width B. Sometimes if the crack, you notice here that the crack is very small, like 0.7 millimeter, and the width is 1.4. So the remaining area is 1.4. The remaining width that will carry the load is 1.4 minus 0.0027. So if you look at it, this is 3 millimeters, like very tiny. So this is approximately equal to 1.4. Because once you have a crack, then you can't carry the load for yielding. And therefore, we're going to ignore that correction and use the entire thickness. And that gives us 4.08 millimeter to resist yielding. We do the same thing for the stronger alloy, which has a higher allowable, and we find that the required thickness for yield is actually smaller as expected. So we would say, well, let's just go with that stronger alloy. Well, we're gonna just have to wait for a minute, because the design will protect here against yield, but is not necessarily protecting against fracture. So we have to do one more step to look at the resistance to fracture, and then we can make the real decision at that point. So when we do that, we find that we have to consider now fracture mechanics, and the first step for fracture mechanics is to find A over B and H over B and find the shape factor. The shape factor turned out to be 1.1. It's very difficult to read here, but assuming that we read it to be 1.1. So the K1 is 1.1. It's the same as an infinite medium, but it's amplified by 1.1. Very small amplification due to the shape. So we have 1.1 sigma square root of pi a. And if we're designing for a safety factor, then this will be our formula. The stress is equal to the fracture toughness divided by 1.1 times the safety factor times the square root of pi a. So to compare, we're just going to assume that the safety factor equals to 1, compare for catastrophic failure, and solve for sigma. And this sigma here for the first alloy is going to be 1135, which is larger than the yield strength, and therefore this alloy is going to yield first. So that's our conclusion here, and therefore we have to stick with the weaker alloy with the yield condition, the condition that we found before, which is the thickness is 4.08 as our criterion, because when we design for fracture, the cracks will require a critical stress that is higher than yield. So yield is going to happen first. For the stronger alloy, on the other hand, the yield strength is 1039, and then when we compute the required stress for fracture, it's only 5 142 and 0.9, and from that we can compute the thickness to be 6.84 millimeter or greater. Obviously, this alloy here, in this alloy, the fracture toughness K1C limits the geometry when we use it, and the required thickness is 6.84 that is required. So it's kind of interesting now that we have found out that weaker may not be worse. So if you have the weaker alloy is not going to fracture, but is going to yield first, and then you can design it with a thickness of approximately 4 millimeters, meaning that the weight is going to be much smaller compared to the stronger alloy, where the thickness has to be greater than 6 plus millimeter. So that shows us a nice example on the competition between requirements for fracture and requirements for yield in loaded components, and that will finish that segment of our failure analysis section.